I wanted to examine the origins of the double-slit diffraction pattern. So imagine that we start with a set of linear waves where the wavelength is constant, equal to lambda, and comparable to the distance between two slits in a boundary. So we have some situation like this, where there's a solid boundary with two slits separated by a distance d. The idea is that the plane waves come from the left side, form circular waves on the right side, and then those circular wave patterns interfere with one another to produce a diffraction pattern. I want to use this setup to come up with the angles at which constructive interference should occur so that, for example, if we were projecting an image onto a screen using light, we would know where the bright spots on the screen should appear. So to do this, I'm going to have to erase some of those waves. They're good illustrations, but it's going to get confusing if I try drawing on top of that. So let me get rid of those, and we'll draw a screen over here to the right. Now let's pick a point on the screen at which we get constructive interference between light coming from the top slit, represented by that light ray, and light coming from the bottom slit, represented by this light ray. We want constructive interference between those two light rays so that the point I drew on the screen will be a bright spot. Well, let me drop a perpendicular to divide this one triangle into two right triangles. And now let's label some of the sides of these triangles. I'm going to label that top hypotenuse for the bigger triangle as L. I'm going to label the side of the same triangle also a length approximately equal to L. Now your first reaction on seeing that picture may be to call shenanigans. How can you have a right triangle that has the same side length as the hypotenuse length? Doesn't the Pythagorean theorem have something to say about that? Well, of course you're right. But imagine that the screen was really far away. So let's pick a very distant screen. My claim is that in that case you can have a side length that is at least approximately the length of the hypotenuse. If you don't believe me, stretch your arms out, and do so in a line that's perpendicular to the line between you and the sun. My claim would be that your right hand and your left hand are each about an astronomical unit away from the sun. The little tiny part of the triangle that would represent the total width of your outstretched arms, not a big deal compared to the length of an astronomical unit. So if the screen is far enough away, we can label both the side of that triangle and its hypotenuse approximately L. Now we haven't quite covered the total distance between the lower slit and the screen. We have that little leftover bit on the other right triangle. My claim is that if we want constructive interference, that has to be equal to n times lambda, where lambda is the wavelength, and n is going to be some integer. If we don't meet that condition, then we won't have constructive interference at the position of the screen. You could get something arbitrary. Maybe if you're unlucky, you would have destructive interference, so it would be a dark spot. But we want constructive interference in order to get a bright spot on the screen. To do that, that little path length difference between the top and the bottom slit has to be n times lambda. Okay. So now we're going to zoom in on the leftmost of the two right triangles because that's the one where we can do some geometry to figure out what these angles have to be. So let's zoom in on that triangle. And the first thing I'm going to do is remind everybody this is a right triangle, so that part is 90 degrees. And let's label the angle over here. It's basically the angle from the horizontal to the base of that tilted right triangle. Okay, we'll call that theta NC. Ultimately, that's the angle that we're going to be solving for. Well, this isn't the world's toughest geometry problem, but there are a lot of angles to label, so let me label the top angle inside that right triangle as psi. I'll label the remaining angle that is not 90 degrees as phi. And so if we do this, we immediately know that because this is a right triangle, psi plus phi must be 90 degrees. Okay? We also know, because phi and theta have to also sum to 90 degrees, the way that I constructed theta, then it has to be the case that theta NC plus phi equals 90 degrees. Well, if two different angles plus phi equal 90 degrees, the two different angles must be equal to one another, right? So theta NC must equal psi. We can take the sign of both sides of this expression, so the sine of theta NC equals the sine of psi. And we know the sine of psi. We can bring over the labels from the left for the distances, but one side of this triangle is d, the distance between the two slits. The base of the triangle is n times lambda. That must mean that since the sine of psi is the ratio of the opposite side divided by the hypotenuse, that sine of theta NC must be n lambda divided by d. We'll take the inverse sine of both sides of this to get the usual expression that theta NC equals the inverse sine of the quantity n lambda divided by d, where once again n is some integer, lambda is the wavelength, and d is the distance between the two slits. So what does this actually look like? Well, if you pick n equals 0, then you can see that there will be a bright spot right in the middle of the screen. If you choose positive integers, n equals 1, 2, 3, and so on, then you'll get bright spots that, the way I've drawn it, would be above the center of the screen. If you pick n equals -1, -2, -3, you would get a set of bright spots at angles located below the center of the screen. You can imagine that this doesn't happen indefinitely. At some point, you'll reach angles that would exceed 90 degrees, meaning that light would not hit the screen, so there are a finite number of constructive spots above and below the midpoint of the screen. Another little detail, this is the derivation for the double-slit diffraction pattern. You can go through a pretty similar process to do the single-slit diffraction pattern, which I won't go through here, but hopefully if you appreciate this geometric argument, you can imagine how it would apply to a single-slit diffraction pattern.